doing? Okay. Right. So looking at that sign-up sheet, it looks like that I have signed up to do question 5, and I did not do question 5 on Tuesday. So I owe you all a question 5. So I suppose that I should do that. Okay, so question 5, unless my memory fails me, asks you to compute the homology groups of this like glued surface thing. So let's start by talking about what this surface is supposed to look like. So I'm supposed to take a surface of genus 2. Let me do my best to draw one. And a Mobius band. Right. And I'm supposed to identify a circle, right, which bounds a disk and the boundary of this Mobius band, and I'm supposed to glue this circle to the boundary of this Mobius band. So, which looks kind of like that, except not really. If I'm being very pedantic, I should label half of this green, and then this becomes green. And then the Mobius band, right, half of this goes this way, if that goes this way, the way that these get identified mentally. So this should go like this. Right. But this is super hard to visualize. Right? So perhaps a better way to visualize what's going on, and this took me quite a while to come up with, is to recall that we have another way to view a Mobius band, and we did this a couple of weeks ago. If I take the bygone representation for RP2 and I punch out a disk in the center, then this is also a Mobius band, right? Because we can, and we did this when we calculated the fundamental group of RP2, right? We took RP2 and we punched out a disk, and then we used the Seifert-Van Kampen theorem on the disk and the Mobius band in order to get the fundamental group here. So now I'm going to glue this center disk that I punched out to a disk here on the surface. And so if I draw maybe a slightly better picture here, right, I have surface, and then sticking out from this surface, I have a cylinder. The top bit of the cylinder having its edges identified like this. Right? But notice that the bottom of the cylinder, right, is not, I did not punch out a disk and then glue this onto the disk. I just identified a disk and glued this onto the disk. So there's no hole on the bottom of this cylinder here, right? This is a smooth thing. Another way that you can think of this, or now that we know that this is the condition, I can now think of taking the surface of genus 2 that has a disk punched out, right? So this is actually now a hole in the space. So this is like S2, 1, right? It's a genus 2 surface with a puncture. And then I can think about identifying a disk in RP2. Right? So this entire space is filled in. Okay? And I can think about identifying a disk in RP2 with the puncture of this genus 2 surface. So there is a, and so one way that we normally draw this, which I should probably draw this in the better way, because this is how people normally draw the punctured surface. So they draw the punctured surface like this, with like the puncture like coming away from the surface, right? So I can think of identifying this puncture with a disk in RP2, right? And so there are a couple of ways that you can compute this homology, but the thing that we should be thinking of is that there's an RP2 hanging out inside of this surface. And the homology for RP2 it's Z for n equaling 2R0. It's 0 for n greater than or equal to 3, but it's actually Z mod 2Z for n equal to 1. So when we do this homology calculation, we will see a Z mod 2Z pop up in the homology calculation, but we shouldn't be too surprised to see the Z mod 2Z show up somewhere because we have this RP2 sitting inside of our space, right? As soon as we took this Mobius band and we glued it to a disk inside of my genus 2 surface, right? I took a Mobius band and I glued a disk to the Mobius band, and that creates RP2, right? So we have a copy of RP2 sitting in here, so the fact that we get a Z mod 2Z shouldn't be too surprising, right? But maybe...
And Jacob, what does that say? N is 2.0?
Or 0, 2 comma 0.
Okay, gotcha. Thank you.
Yeah, maybe I should have written it as a 0 comma 2 to be more better. Right. So the way that I'm going to do this homology calculation is I'm going to do,
yeah. While we're clarifying, it's Z mod 2, what was that?
Z mod 2Z. Yeah.
Okay, cool. That's what I was wondering. Thank you.
Or some people just write this as like Z sub 2. Okay. But I want to be explicit because we're going to be talking about like Z plus Z plus Z plus so Z to the 4 and like other terms.
Cool.
Okay.
Awesome.
So the way that I'm going to do this is I'm going to use Meyer v. Torres, and I'm going to do this using these two spaces up here, just because that's what the problem kind of implies how you would do this. And unless you spend quite a while like playing with this to realize that you could also do it this way, right? That's probably how you're going to approach the homology. However, as an exercise, compute the homology from this point of view. It's actually easier. So once I do this, you will see what kind of steps you need to do and how you're going to set this up. And if you do those same steps in the same setup, except with the punctured the punctured genus 2 surface and RP2, you're going to get a disk in there, and that's going to make more homology 0 than in the example that we're going to do, and it's actually just going to make the algebra easier to do. And if we have time at the end of the day, I can just do this exercise and show you that it's easier. But yeah, so, okay. So first, let's note that the homology sequence of the annulus is the same as the homology sequence of the Mobius strip, which is just the homology of the circle S1, which is Z for Q equal to 0 or 1, and it's 0 for Q greater than or equal to 2. Right? And that's because both the annulus and the Mobius band deformation retract onto the circle. Right? So for the annulus, this is pretty clear, right? You just choose one circle and you just collapse to one of those circles. For the Mobius band, and I'll scroll up to the Mobius band real quick, you just choose like this center band, right? It's also called like the core. And you just deformation retract both of the edges down onto that center circle. So both the Mobius band, or you can think about just like deformation retracting this interior circle out to the edge. And then you just have like two edges that are identified. And then when you identify the edges, you get a circle. So both of these, both the annulus and the Mobius band, deformation retract S1. So let C be the circle. We glue the Mobius strip 2. And let's denote the Mobius band by capital M, right? Also, let's denote the Mobius band, not the Mobius band. Let's denote the genus 2 surface by T2 sum T2. Is everyone familiar with this notation? Have people seen this notation before? Okay, some people haven't. So the way that you form, so this is something that you can do with manifolds of equal dimension, is this product here. What you do for this product, so we'll just do an aside on the side here. To form X sum Y between manifolds, I'll say n manifolds X and Y, you remove n ball from each, then glue along the boundary. So in this case, I have a torus and a torus, right? I'm gonna remove a disk or remove a ball, so that way I'm left with the boundary of a disk, and then I'm gonna attach these two disks together. And then if I think about like stitching together what I just attached by like pulling at the stitching, which brings the two things together, right? I get exactly the genus 2 surface. Right? And so there's a classification theorem for surfaces that says that any orientable surface is either a sphere, a RP2, or it's a connected sum of tori with or without a copy of RP2. Because if you stitch together like two copies of RP2, you get like 3 tori or something like that. So yeah, so this is like a pretty standard way to talk about surfaces of a particular genus, because the 2 genus is just 2 stitched copies of tori, and the 3 genus surface is just 3 stitched copies of tori, etc. Okay, cool. So we're going to let you be an open annulus around C in T2 sum T2. And we're going to let V be an open annulus around C in V. So let me draw some of these pictures again. Right. So I have the 2 surface, right? I have the curve C that I'm going to identify here. And I have my Mobius band, which I'm drawing like this. And I have the curve C that I'm identifying in the Mobius band. So U is going to be an open annulus around C in the surface. So this here is U. And V, use even another color, is going to be an open annulus around C in the Mobius band. Right? So that's V. Okay. Put A equal to the surface union V, and put B equal to the Mobius band union U. And finally, we're going to note, and this is like the extent of the setup, we're going to note that the intersection of A and B is exactly equal to the union of U and V. Okay. So I kind of have an idea of what A intersect B is going to look, or of what A and B are going to look like. So if I draw, right, the surface that I'm kind of looking at here with that version that I've already shown, right, like this. So let's see. A is going to be the entire surface plus a little bit of the cylinder that's sticking out, right? So A kind of stops here, right? That's what A does, right? B is going to be the entire Mobius band plus like a tiny bit of the surface. Like B is going to be like this part. And then the intersection is going to be here. So the intersection, if I try to draw like A intersect B, let's see, using the same colors that I used up here, I have like part of the cylinder that goes like around like this that goes down. And then I have like part of this blue annulus that it's like attached to. So like the interior is like this, but that looks like really hard to see. So instead, I'm just going to draw it like this. And then rotate this picture around the y-axis. Right? And then you get the same picture that I was trying to draw here. Right? So if you rotate this around the y-axis, you should get, right, an annulus, right, the blue annulus that was U with the V thing that's sticking out. Right? So the V thing is this orange bit, right? And the blue annulus is what you get when you rotate this blue bit, right? And that's what this should more or less look like. Right? Does that make sense to everybody? Like, can you imagine like rotating this thing around the y-axis? Right? You get like a annulus sitting on the bottom with like a orange V sticking off the top of it. Okay. So the annulus around this punctured circle here, right? The boundary of this annulus is C. But for this annulus, the center of the annulus is C. Right? People are frowning at my images, so maybe let me. So if this is my annulus U, V sticks out of this like this. Right? And this goes here, and this goes here. Right? And then my center circle that they share is this center circle here. So I can keep attempting to draw pictures until people are like happy, but I don't know, that might not be. Right? And so like if you take this picture here, you rotate it around the y-axis. Right? So like I've drawn this with like this the x-axis, this the y-axis, then you should get something that looks kind of like this. And the point that they meet, which is the green point, should be like this point here. Maybe it's just hard to see because it's hard to see on your screen. Maybe I can like zoom in and then like move over. I don't know. I don't know. Does that help? Am I just doing something? Okay. Yeah, so like if you take this picture, right, and you rotate this picture around the y-axis, you should get something that kind of looks like this, except maybe it's easier to visualize because like you're the one constructing the mental image from something more explicit instead of me trying to draw my mental image, and then we're relying on my art skills, and I did not go to art school. Okay. Okay, so at this point, you might be like, Jacob, why are we doing this? Why are we here? What's the point? Those are very reasonable questions to ask. So I set up this A and this B, and I've drawn this A union B. And maybe I should note that based on this picture, U intersect B is equal to this tripod that I've drawn over there, right? Cross S1, but that's just S1 basically, right? Because the first component deformation retracts to a point, right? And so I just get S1. And so the reason that I'm making these identifications is because I want to use Meyer v. Torres to compute the homology groups of this space. So in order to use Meyer v. Torres, I need to find a capital A and a capital B, so that way the union of the interiors of A and B is the entire space. And so that way I know what the homologies of A and B and the intersection are, right? But also note that up to homology, A is homology equivalent to just the genus 2 surface, because I can just take the little bit that is the cylinder, the open cylinder, and deformation retract that annulus down to the boundary circle on A, right? I don't know if I should draw more pictures, but A is the entire surface plus a little bit of the cylinder, so you can just collapse the cylinder onto that boundary circle C. Cool. Similarly, B is, at least up to homology, the same as just the Mobius band, right? Because I can just take, right, right, B is the Mobius band plus this annulus U, and I can deformation retract the annulus U to that boundary circle C, and then I just get the Mobius band with this boundary circle C, right? So, okay, so the first thing, so now we're going to compute the actual homology using Meyer v. Torres. And the first thing that I'm going to say is that.
Sorry, Jacob. Okay, I was mainly with you. So there's a hole in the top of that cylinder, like to get the Mobius band. Like there's a hole in the RP2 part.
There is not a hole in the RP2 part because these two edges are identified with each other, right? I drew them as red so that way you'd look at like this picture, right? But so this picture I've drawn as an annulus with like a hole punctured in the center. But you could think about stretching out the middle part so that way the punctured hole is at the bottom and the red bit's at the top. Right? So like here, and I'll draw this big because apparently this is hard to see. Right?
I think in the picture I'm seeing B is just RP2, but it's not just RP2.
Yeah, it's here, I can draw this big. So here is my Mobius band with C as my bottom circle, right? And then on this bottom circle, I have a little annulus around C. The annulus lives in the surface. And this is B. And so in order to get B, which I'm saying is the same up to homology as M, I'm just going to deformation retract this bottom annulus to this bottom boundary circle. right? By just collapsing the two boundaries of my annulus to the circle.
So like I'm remembering when we did RP2, like when we calculated that, and the Mobius strip was like that part around, like it was so you cut out the middle and the part around
exactly.
it. So is this like squished into that picture or?
Yeah. So yeah, so what I did here was I took this, right, which is right. This is RP2 with a center disk cut out, and that's a Mobius band, right? And all that I'm doing is that, so like if I did this with an annulus, right, just take an annulus and pull at the bottom circle and leave the top circle fixed, and what you'll get is a normal cylinder. Right, so does that like if I just have a normal annulus, right, this goes like this, and I pull at the bottom circle, then I get just a cylinder with neither the top or the bottom filled in.
Okay, so basically like,
or just think about like looking down a tube, and that kind of looks like an annulus, right? You have like a small circle in the middle, which is the circle that's far away from your eye, and a big circle, which is the top of the tube that you're looking at, the inside, which goes between those two circles.
like if I were gonna draw the black lines of the cylinder on your picture on the far left, they would be like little partial radii, right?
Yeah. So.
Okay.
Yeah.
I think
if these lines are these lines.
Yeah. Okay. Yeah. Which are the same black lines in like the center picture.
Yeah, exactly, as these black lines. Yeah. Yeah. And so and I don't know, I spent quite a long time trying to like look at like this picture, right? Which is like another way that people draw the Mobius band, where they like try to do like some sort of clever drawing in order to like make this look like it's rotating. But then you have to think about like identifying this entire boundary circle to one circle. And I could not figure out how to do this mentally. Like the only way that I could draw a reasonable picture of this was to draw the Mobius band like this. That was supposed to do like this, right? And then just be like, hey, now the boundary is an actual circle, and I can just drop it on top of, yeah. Okay, cool. So I'm gonna try to.
Okay, sorry, I have a really dumb question really quick. You had isomorphisms written above, and then you have B squiggle line M, and you said something about homologies, but what does that symbol mean?
Yeah,
symbol in
so
between M and B.
Yeah, so this means homology or homotopy.
Awesome.
Homotopy equiv.
Cool. That's right. Okay.
Yeah.
Okay,
and
cool.
In general, when this means like homeomorphism.
Okay.
When you have like two lines in the squiggle.
Okay, cool. Awesome. Thank you.
Okay.
And then
so I'm gonna try to move all these pictures over to the side so that we have room to write. Okay, Davey, did you have another question? I thought I heard you say the word wait. Okay, either you're muted or you didn't have another question. Okay, so we're going to try to use the Meyer-Vitor sequence to compute what the homology of this is. We do get one homology for free, right? The first homology, or the zeroth homology, excuse me, is equal to 0, or sorry, is Z, the zeroth homology. 0 is equal to 0, Jacob. The zeroth homology is Z because this entire space is path connected, and we talked about how for zeroth homology, it's just generated by the path connected components, right? So because the space is path connected, we just get the zeroth homology for free, right? We don't have to wait. Okay, so now we use Meyer-Vietoris for q greater than or equal to 3. So first off, this is a surface, and I'm gluing another dimension 2 space to this. So this has like no 3-dimensional bits, right? So we should expect the 3 and higher homologies to all be 0, right? Just like our intuition should be telling us that like homologies of 3 and higher for this space should be 0, right? Because, and if you read that post that I uploaded, there's no 3-dimensional spaces that I can fill up, right? That I could like fill, like with that balloon analogy that was on that post that I put on the website. But like in general, like you wouldn't expect like a line to have 2 homology, right? Because there's no faces in a line to generate any chains, right? To make the chain map, and then you take a quotient of the chain map to the homology map, right? So there's no 3-dimensional spaces, so I can't put 3 simplices in this space. So there are no 3 simplices to generate any groups to take a quotient of to make 3 homology and higher. But to formalize this, okay, I have that for q greater, no, I already said for q greater than or equal to 3, right? All right, so here's a piece of Meyer-Vietoris, right? And this becomes the qth homology of the genus 2 surface, direct sum the qth homology of the Mobius band, going into the qth homology of X, which we don't know. And then this goes into the q-1 homology of the circle, right? Because that's what we determined A intersect B is up to homotopy equivalence. But for q greater than or equal to 3, this homology group is 0, this homology group is 0, and this homology group is 0. Right. So here I have the sum of 2 homology groups, and the only way that I can have an exact sequence with 0 something 0 is if this thing here is 0. By the way, I suppose that I should remind you, so reminder. HQ of S1 is Z for Q equal to 0 or 1, and it's 0 else. And this is the same as the homology group of the Mobius band, as I said above. And HQ of G tori, which is the genus G surface, this is Z for Q equal to 0 R2. It's 0 if Q is greater than or equal to 3, but for Q equals 1, this is Z to the 2G. And you can compute this yourself, either by using Meyer-Vietoris again, or you can remember that, like, for example, T2 sum T2, it has a representative oh boy, I made that side too short. It has a representative polygon where this is like A1, A1, B1, B1, A2, A2, B2, and B2. And in fact, you can just stack these along as much as you'd like, actually. Just for talking about it now, let me make it bigger so that way you all can copy this down correctly. Oh, geez. Making my handwriting bigger did not make the handwriting easier to read, even if it made the picture easier to read. So this is B2. And so the way that most people draw this is like they draw this as an octagon. I'll try to clearly label the vertices so that way it's obvious that this is an octagon, right? And you have 4 in a row going clockwise and 4 in a row going counterclockwise. And then you label these so that way they form tori as you go from the 2 opposite points going down. So this becomes B1, A1, A1, B1, and so that's the first 4, and the next 4 you do B2, A2, and A2, B2, and etc. And if you just do like the chain homology on this octagon, right, the boundary of the only face that you have here, right, if you go around once, you get every edge with positive orientation, and then you get every edge with negative orientation. And so the boundary map on the face goes to 0. And because all of the vertices are identified, the boundary of every edge goes to 0. And so if you just calculate from the chain map, right, if you just calculate like C3 and C2 and C1, and then you do the quotient of kernel mod image, you'll get exactly this. Right? Because the chains are exactly equal to the homology because all of the maps, all the chain maps are 0. Okay. I think I've spent enough time belaboring this point. But I suppose that I should pause and ask if there are any questions about this bit before we move on to continue the Meyer tours. Okay, so again, I'm gonna try to make this smaller but readable, and I'm gonna try to keep it for posterity. Okay, cool. So we have computed the high homology for, right? So to get back to what we were doing, this space is 0 homology for q greater than or equal to 3, which is exactly what we thought was going to happen, because you can't put any 3 simplices or 4 simplices or 5 simplices in this space. Right? Okay, cool. Now let's do the tail end. This is the hard part. So we have that H2 of the intersection goes to H2 of the sum of the components, which goes to H2 of X, which you can think of as the union of the components. And this goes via the boundary map to H1 of A intersect B. And I'm just going to write equals here instead of a line. So I'm just going to rewrite H1 of A intersect B. This goes to H1 of A direct sum H1 of B, which goes to H1 of X, which goes to H0 of A intersect B. If this is equal to H0 of A intersect B, this goes to H0 of A direct sum H0 of B, which goes to H0 of X, which goes to H-1 of A intersect B. But of course, that's the same as 0. Okay, so this is the tail end, and I'm going to now insert what A intersect B and A and B are all equal to. So I'm going to write the same thing just with the i.e. I have H2 of S1. This goes to H2 of the genus 2 surface plus H2 of the Mobius band. This goes into H2 of X, which goes into H1 of the circle. I'm going to give myself some space so that way I can write things in. I get H1 of the circle. Okay, now I'm just copying everything with 1s instead of with 2s. And I'm going to give myself a lot of space between these things so that way I can write in between these things. Okay. And also, because this is going to be useful for later, I'm going to label some of these maps. So I'm going to label this map I2, I1, I0. Over here, this is going to be J2, J1, and J0. And over here, I'm going to have the second boundary map, the first boundary map, and the 0th boundary map. And then let's go ahead and fill in the stuff that we know. So I know that this here is 0, this is Z, and this is Z. And because I wrote the qualities, this is Z, and this is 0, right? So those are all of the information from the circle.
Sorry, isn't H0 of S1 Z?
Oh, yeah, sorry, I meant to write the same thing
Yeah.
as I wrote over here. Thanks. Thank you. Also, the Mobius band is a circle, right? So its second homology is 0, its first homology is Z, and its 0th homology is Z as well. So that's all the stuff that I get from knowing what the circle is. Let's do in green all the stuff that I get. So this here is going to be Z. This here is Z to the 4. And this is Z. Okay. So now I have to figure out, oh, and from our aside before, I know that this is Z, right? Because it has one path connected to one. So I just have to figure out what H2 and H1 are. Easier said than done, Jacob. Okay, so the first thing that I want to note, this is supposed to be blue. You're supposed to be black. Come on, don't stop being. So note that I1 is injective. And you might be like, Jacob, I don't know that it's injective yet, right? Because normally in order to tell that something is injective, I have to go back from the prior map and go, hey, is this 0 going into this thing? Okay. But I could determine that I1 is injective because I know what I1 does, right? It sends the generator here, right, into that generator, comma, the negative of that generator, right? I know what I2 does. We've talked about this before, right? It sends V to V, comma, minus V, right? That's what the map does, right? And if I look at this explicitly, right? If V is the generator for H1 of S1, and I'm going to say W is the generator for H1 of the Mobius band, then we have that I1 of V is equal to 2W. Right? And that's because of the relationship between this boundary circle and the Mobius band. So what I'm doing, if this is the Mobius band, right, which does this, then saying W is the generator of the Mobius band means that this red edge is W, right? Going once around W gives me a boundary component for the Mobius band. And this is the boundary circle as part of the Mobius band, but this boundary circle is the S1, right, that I'm talking about from this inclusion map, right? So that means that this going around once, this circle, this is V, right? And if I view V as an element of the Mobius band, if I just deformation V up to the edge, I get the relationship that V is equal to 2W. Right? So, you just move V out to the edge and you go going once around V. Well, that's the same as like having my green edge start here and going all the way around this. But this edge is W and this edge is W. So I go around W twice. Right? It's the same kind of trick that we did when we computed the fundamental group of the Mobius band. Right? We got this like degree 2 thing coming from the Cipher-Van Kampen theorem because it's the same idea. I'm including the circle into the Mobius band and I get this degree 2 map. It's not actually, yeah. I get this like factor of 2 inside of my map. But this map, thus, and actually this is like 0, 2W. Because I2 goes into an ordered pair. Right? So I should be more explicit about this. So let me clean that up. But that's the hard part to understand why this is 2W, right? But now you might be saying, okay, cool. I understand why V goes to 2W in the second component here, right? It goes to 2W in this component. How come it goes to 0 in this component, Jacob? Well, in the second component, right, I have that I'm including my boundary circle into this space. But if you read the problem again, this circle is the boundary of an entire 2-disk. So all that I can do with this circle is I can just deformation retract it to the center of the circle. So this one boundary goes away. It collapses to no boundary, right? Because it's not a boundary for anything in my one circle, right? So for the first component, when I include V into the surface, right? When I include the circle into the surface, it's the boundary of a disk, right? That disk just collapses to a point, right? So that's why this V goes to 0, right? So even though this is what the map does, what we have just determined is that this V goes to 0, 2W. Or negative 2W, depending on, yeah. I should probably put a negative in here because I said that I have to put a negative on it, and that's fine. Right. So this V collapses because it's the boundary of a disk in a surface, which is not a boundary component for homology, for first homology. And it goes to 2W because of this relationship here with the Mobius band. Okay, are there any questions about that bit? Because the rest of this bit is just standard Meyer-Vietoris stuff, right? But the fact that V goes to 2W is where we are eventually going to see this, where did I say it? At the very beginning. Yeah, when I said this homology is Z mod 2Z, this fact that we have this factor of 2 is exactly where this Z mod 2Z term is going to come up, the fact that we have this double behavior. right? So that's what's going to happen. Okay, cool. Anyway, this, which is injective, right? Because this is a map, right? It's a map Z to Z4 plus Z, right? So this is injective because every integer gets mapped to -2 times that integer in the second component, and you can use that to show that this map is injective. Okay, cool. So thus, the image of the second boundary map is the same as the kernel of I1 because the sequence is exact, which is 0. So D2 is the 0 map. Thus, the first row becomes 0 maps by I2 into Z direct sum 0 by J2 into H2 of X via the 0 map, which is D2. So because this is the 0 map, I can put a 0 here. Right. Which means J2 is an isomorphism i.e. H2 is isomorphic to Z. Right? Because Z plus 0 is Z. So H2 is isomorphic to Z. Okay. Also, note that the image of I1 is 0 plus 2Z. Right? That's pretty clear based on the fact that this is what the map does. Right? Right. Similar to the above, I0 is injective, which means that the first boundary map is the 0 map. And so the second row becomes H1 of S1 maps via I1 to H1 of the genus 2 surface plus H1 of the Mobius band, which maps to H1 of X, which maps via D1, I should put J1, which is the same as the 0 map into 0. Right? So filling in the stuff that we know, right? This becomes Z maps via I1 to Z4 direct sum Z, which maps via J1 into the space that I don't know yet, which maps to 0 via the boundary map, which is the same as the 0 map. Okay, so the image of J1 is the kernel of J2, J1, because this is an exact sequence. And as I just noticed, this is 0 plus 2Z. The image of J1 is the kernel of this boundary map, which is 0 because it's the 0 map. So J1 is surjective. No, that is not the right word, right? No, the image of this is not this. It's all of H1 of X, because the kernel of a zero map is the entire boundary map. So this is surjective. Sorry, my notes were wrong for that note. And this is the weirdest part of this problem. Thus, by the first isomorphism theorem, I was so mad when I figured out that this was the first isomorphism theorem. It was like 10:30 p.m. that Monday. And I was like, I can't believe that I have to use group theory. How dare this problem make me use group theory to solve this? Anyway, so thus by the first isomorphism theorem, right, H1 of X is isomorphic to Z4 plus Z mod the kernel of J1, which is the same as Z4 plus Z mod the image of J2, which is the same as Z4 direct sum Z mod 0 plus 2Z, which is exactly Z4 direct sum Z mod 2Z. Some people would write this as Z4 plus Z2, but the 4s and the 2s are in different places. So therefore, by the work that we have shown, HQ of X is Z if Q is equal to either 0 or 2. It's Z4 plus Z mod 2Z if Q is equal to 1, and it is 0 otherwise. And that's what the homology of this space is. I told you that it was going to take a while. I also told you that this is easier if you do it the other way. If you look at the punctured 2 surface and the Mobius band. And just to outline what that looks like just a second, the other way. A is equal to the surface of genus 2 with 1 puncture. B is equal to RP2, and you get that A intersect B is just a disk. And because this is a disk, this becomes nice. So what you get is that the nth homology of the disk goes to the nth homology of RP to sum the nth homology of the 2 surface. And okay, actually, because of the overlap, right? The way that these overlap, when you do A, you have to do A and sum of the other space. So you can choose the other space to be that entire, to union with the entire disk. So you don't actually need to know the second puncture. Anyway, and then this goes into Hn of X, which goes into Hn minus 1 of the disk. And as long as you are above, and right, like the homology for the disk is 0 except for n equals 0. And so you just get that these are isomorphisms. Okay, but like I just said, if you look up at what the homology is for RP2 at Q equals 1, you get Z4 from the surface and you get Z mod 2Z for RP2. So you get exactly this at Q equals 1, right? This equation gives you exactly this at Q equals 2. And then you get to ignore the Q equals 0 case because again, it's path connected. So this is actually easier if you play with this surface enough and you do the Meyer-Vietoris formally for the RP2 case and the punctured sphere case. But I'm gonna let you all do that. And then the last thing that I'm gonna say about this example is that what are you supposed to do for this example if you did not know what the homology of the two surface was, right? Like what were you supposed to do for this problem if you did not know this homology? Well, if you didn't feel comfortable with this argument using the chain map, you could have also used Meyer-Vietoris to solve for the homology of the two surface. And if you tried to do that and you didn't know what the homology was of those two spaces, you could use Meyer-Vietoris to find those homologies, right? Like and so I said on Tuesday that in order to solve this problem, I had to ask one of the sixth years who study topology for help for this problem. And he was like, Jacob, why are you having them go to the chain map to do this? You should just have them do another Meyer-Vietoris problem, because you can. So I did this, and it's not fun, but we can do it in like office hours or a future day if you'd like, but maybe there are more important things for you to focus on. But I would like to point out that that is not like the number one strat. The number one strat is not to throw enough Meyer-Vietoris at a problem for you to be able to solve problems. But that is the backup strat, right? If you're sitting in the topology qual and you're like, I have an hour and a half and I only have to do this one algebraic topology question, and you don't know what else to do, you can, for all of the spaces that would be reasonable to ask you to compute on the qual, you can eventually throw enough Meyer-Vietoris at a problem to turn the problem into disks and circles. Right? Because like if you wanted to do like Meyer-Vietoris with the two circles, then you'd be like, okay, I have this torus with a circle punctured, and I have this torus with a circle punctured. Right? So in order to do Meyer-Vietoris on this, I need to know the homology of the intersection, which is the circle, and I need to know the homology of the punctured torus. Well, I don't know what the homology of the punctured torus is, so can I figure out what the homology of the punctured torus is using, well, okay, the punctured torus is homotopy equivalent to, right, the figure 8, right? There's a deformation retraction if you draw the torus, right, like this, right? Then removing a circle is the same as removing a circle from the interior. And if you play with this, right, you deformation retract this to just a square, so it has no center, right? And then you identify this, and you get like, this goes this way, and this goes this way, I think, if I did this correctly, right? And then you like glue these two circles together and you get the figure 8, right? Okay, and then you're like, okay, what's the homology of the figure 8? Well, in order to figure out the homology of the figure 8, use Meyer-Vietoris on two circles where the intersection is a point, and hopefully you know the homology of a circle and the homology of a point, right? And so you can do all of this problem, and if you want to figure out what the homology of, right, of like RP2, right, you can figure out the homology of the RP2 by using Meyer-Vietoris, right? So it's not your first line of action, should not be to throw 4 Meyer-Vietorises at a single problem to do it. But, you know, like I said, if you have an hour and a half and you just are trying to figure out a homology problem, you could just keep throwing Meyer-Vietoris at a problem to turn it into circles. Okay, so this took longer than I thought it was going to take. Are there any questions about this problem? I imagine that there are many, so feel free. You won't hurt my feelings at all if you have lots of questions, because I was not there. Yeah, I can't believe that this was a qual question. Took this long to do, but if you had done lots of Meyer-Vietoris questions like this, it would have taken you a lot less time to set up these spaces like I did and draw these. You wouldn't have to draw all these pictures and stuff. So, you know, if you just read the argument, this is like a page, maybe two, of breaking it out. So.
I mean, not directly related to this problem, but as you point out, right, it's one could theoretically compute the homology of all these individual spaces that we use for this problem, or you could memorize them, which I think is the expectation.
Yes.
So besides like SN, RPN, genus G surfaces, any other homologies that we should know?
The wedge of two circles comes up a lot. Yeah. Yeah, and RPN is probably one that I should. Okay. So if you've looked at the exercises to know document lately, if you've opened it, you'll notice that I replaced, so I'll write it here so that there's a record for the future. I replaced part B, question 4. And Anthony was kind of alluding to this in office hours, and we talked about it, and I convinced him of the wrong thing, that this old question 4 was correct. But you came in office hours and you asked me about it. I think Shanna's also come to office hours to ask me about this old question. And I was just like, no, yeah, you can use like this deduction argument. Well, Raul also brought it up yesterday on the Discord. Not everybody's a member of the Discord, but if you are, here's a counterexample to
I was
old
literally going to ask you about this in office
question
hours
4
tomorrow.
With finite trees. Right, so versus those are the two spaces. These two spaces have the same number of valence 1 and valence 3 vertices, right? They both have 4 vertices of degree 3, and they both have 6 vertices of degree 1 and no other vertices. But if I remove this vertex, right, removing the center vertex gives 3 components, each containing a vertex of degree 3. But any removed degree 3 vertex here has 3 components at least one does not have a degree 3 vertex. So therefore, these two graphs are not homeomorphic. Because every time someone's come to my office hours to talk about this problem, I'm like the first time I was like, oh, you have to also include the degree 1 vertices. It can't just be degree 3 or bigger. Oh, you can't have infinite graphs. It only works for finite graphs. Oh, you can't have loops. You can't have a an edge that connects a vertex to itself. And, like every time this problem became more and more constrictive. But I think that this counterexample with trees really just puts the nail in the coffin. There's no way to make a graph nicer than to ask that graph be a tree. So this problem is just super wrong. I talked to Jonathan, who's the one who wrote this problem. He said, and I quote, "I think I must have been on crazy pills when I wrote this problem." So he's removed it from his list of problems to know. I've removed it from my list of problems to know, because this is not a problem to know because it's wrong. So instead, I've replaced this with a problem that just says, hey, you should know the homologies of these basic spaces. It's exactly the list that Anthony just said, because those are the spaces that you refer to compute other homology. And if you haven't computed them before, feel free to try to compute them. You can use Meyer v. Torus, and if you know like the point and the circle, you can use Meyer v. Torus to compute the rest of them. But really, you should just have those lists memorized. Okay? And I'm going to update it to add RPN, because I think that knowing RPN is reasonable. But I also think that a qual question asking you to compute the homology group of RPN would also be reasonable, because, so scroll all the way up to the homology group of RPN, it has this Z mod 2Z here. So being able to compute the homology group of RPN and show where that Z mod 2Z comes from, I think would be a reasonable qual question. So the rest of them you should just memorize, but for this one, you should also know how to do it. Cool. It's 9:50, so technically class is over. I'm going to go ahead and end the recording. So goodbye if you're watching this on YouTube. If you have any questions, feel free to stick around and ask. Otherwise, I have office hours tomorrow, so you can come then.